Hello and welcome to MyScience Tutorials. In today's video, we are going to be looking at how to calculate pH and pOH of a solution. So before we start, if you are new to MyScience Tutorial, kindly consider subscribing as we post daily video on biology, chemistry, mathematics, and physics. So let's start. So we want to start by looking at the self-ionization of water, or auto-ionization of water. Now, water is said to be an amphoteric substance, which means it has both basic and acidic properties. So in the presence of an acid, it behaves as a base, and then in the presence of a base, it behaves as an acid. So water, upon dissociation on its own, so we have 2 moles of water dissociating. So we have 2 moles of water, which is liquid. Okay, then upon dissociation, it will give us what? Hydrozonium ion, okay, in solution, and hydroxide ion in solution. Now from this we can get what we call the ion product constant, Kw, okay, which is equal to what? The product of the concentrations of the hydrozonium ion in solution and then the hydroxide ion in solution. Now at room temperature, which is what? 25 degrees Celsius, the concentration of the hydrozonium ion in solution is equivalent to the concentration of the hydroxide ion solution, which is equal to what? 1.0 times 10 raised to the power minus 7 mole per dm cube. Okay, so if this holds true, it means our Kw is equal to what? 1.0 times 10 raised to the power minus 7 times another what? 1.0 times 10 raised to the power minus 7, all giving us what? 1.0 times 10 raised to the power minus 14 mole square dm minus 6. Okay, so this is the value of our Kw. Now let's make this equation 1. Another very important equation we need to note before we go on to see how to calculate pH and pOH is what? pH plus what? pOH is equal to what? 14. This is also very important. Now the pH of a solution is given by what? The negative logarithm of the hydrozonium ion concentration in the solution, or pH can be written as what? Log of what? 1 over H3O plus ion concentrations in solution. So let's take this as our equation 3. Now pOH on the other hand is the inverse. So we have negative logarithm of hydroxide ion concentrations in solution, or pOH is equal to what? Log 1 over what? OH minus ions in solution. So this is our equation 4. So basically we are going to be using any of these equations to solve problems in the upcoming examples that we are going to look at. So basically our Kw, which is the ion product constant, is defined as what? The product of the hydrozonium ion concentration and then the hydroxide ion concentrations in an aqueous solution at what? A constant temperature, which is what? 25 degrees Celsius. Now with this basic introduction, let's have a look at a practical example. So we have example number 1. A solution has a pH of 5.78. Given that Kw is equal to 1 times 10 raised to the power minus 14 mole square dm minus 6 at 25 degrees Celsius, calculate the hydroxide ion concentration of the solution at this temperature. So this is the example we are going to look at. So first of all, let's write down our parameters. So we have our pH given to us as what? 5.78. Then we have our Kw is equal to 1 times 10 raised to the power minus 14 mole square dm minus 6. Now we have to calculate the hydroxide ion concentration, which is the OH minus ion concentration in solution, which we do not know. So let's start. So first of all, we are going to use the pH value we have over here to get the hydrozonium ion concentration in the solution. So we have pH is equal to negative log what H3O plus in solution. So we have 5.78, which is the value of the pH, is equal to what log 1 over what H3O plus ion in solution. Now note, log is always with the base 10, so the 10 will come and raised to the power 5.78 to get rid of the logarithm over here, the first law of what logarithm. So we have 10 raised to the power 5.78 is equal to what 1 over H3O plus ion concentration. So making H3O plus ion concentration the subject, we have what 1 over, then this will become, this will not come here, this will come here, so we have 10 power 5.78. So from there we can say our hydrozonium ion concentration is equal to 1 over 10 raised to the power 5.78 is equivalent to what 1.659 times 10 raised to the power minus 6 mole per dm cube. So this is the value of the hydrozonium ion in solution. Now the question is asking us to find the hydroxide ion concentration, but we know that Kw is equal to the product of what the hydrozonium ion in solution and then the hydroxide ion concentration in solution. But we know Kw is given to us over here as 1 times 10 raised to the power minus 14 is equal to, we have this value which is what we have here, 1.659 times 10 raised to the power minus 6 multiplied by what we are supposed to find. So making the hydroxide ion concentration the subject, which means we have OH minus as the subject, it means we are going to divide the Kw, which is 1 times 10 raised to the power minus 14 by 1.659 times 10 raised to the power minus 6. Then our hydroxide ion concentration is now equal to 6.03 times 10 raised to the power minus 9 mole per dm cube. So this is the concentration of our hydroxide ion in the solution for this particular example. Let's have a look at another example to further understand to further enhance our understanding on how to calculate pH and pOH. Example number 2. So we are to calculate what the H3O plus hydrozonium ion concentration, the NO3 minus concentration, and then the OH minus concentration in 0.009 molar nitric acid or HNO3. If 100 cm cube of what 0.009 molar nitric acid is mixed with 100 cm cube of 0.01 molar sodium hydroxide solution, will the final solution be acidic or basic? And then justify your answer in II above by calculating H3O plus of the solution mixture, given that Kw is equal to 1 times 10 raised to the power minus 14 mole square dm minus 6. Alright, so let's have a look at the first part of the question. So our we have to find what the H3O plus hydrozonium ion concentration if this and this, if nitric acid dissociates in water. So we have HNO3, okay, aqueous plus water, which is what liquid. So this will give us what HNO3 is an acid, so water will behave as a base. So it's the nitric acid will donate a proton to the water. So we have H3O plus in solution plus what the NO3 minus aqueous in solution. Now initially, before the reaction proceeds, we have what 0.009 molar of the acid in solution, and as at that point the reaction has not occurred, so we have 0.00 0.00 concentrations of these ions in solution. Now, after the reaction has occurred, all the acid will be used to produce the hydrozonium ion in solution. So we are going to have 0.000 molar of the acid left, and then we are going to have what, 0.009 molar of the acid H3O plus produced, and then the same concentration, 0.09 molar of the NO3 ion produced in solution. So from this we can say what the concentration of what H3O plus hydrozonium ion is equivalent to what the NO3 minus ion, which is equal to what, 0.009 molar. So it means this and this we've already calculated it, and this is what we have. So the concentration of these two are what, 0.009 molar. Now let's move on. Now we have to find the concentration of the hydroxide ion, but we know Kw was given to us as what, 1 times 10 raised to the power minus 14. Okay, so Kw is equal to what, H3O plus ion concentration, and then OH minus ion concentration. Now we have our H3O plus ion concentration as 0.009, so we just substitute that into the equation. We have 1 times 10 raised to the power minus 14 is equal to 0.009 times OH minus. So making OH minus the subject, we have OH minus is equal to 1 times 10 raised to the power minus 14 divided by 0.009. So this will give us a value of what, 1.1 times 10 raised to the power minus 12 molar. So this is the concentration of our hydrozonium ion in solution. Now let's move on to the II aspect of the question. Now the II is saying if 100 cm cube of the acid is mixed with what, 100 cm cube of 0.01 molar sodium hydroxide, what will be the acidity or the basicity of the final solution, whether it will be an acid or a base. Now nitric acid is a strong acid, sodium hydroxide is a strong base. So together in solution, depending on the one that is the limiting reagent, that will determine whether the resulting solution will be acidic or basic. What do I mean? We have the acid, okay, reacting with the base, sodium hydroxide, aqueous, to give us this product. We have the sodium will react with NO3, so we have this produced as our salt plus water, which is liquid. Now for the acid, I'm going to use the concentration as Ca, the volume as what, Ca. So the concentration of the acid is what, 0.009. Then the volume of the acid is what, 100 cm cube, which is equal to 0.1 dm cube. Now for the base, the concentration of the base is what, 0.01 molar. Then the volume of the base is what, also 100 cm cube, which is equivalent to 0.1 dm cube. So from here we need to calculate the moles of the acid that reacted with the moles of the base to see which of them is in excess. But we know what, concentration is equal to mole over volume. This implies our mole is what, concentration times volume. So our what, mole of acid is Na, is given to us by what, 0.009 times 0.1. So our mole of acid is equal to 0.0009 moles. Now the mole of the base will be given to us by what, 0.01 times 0.1. So our mole of the base is equal to what, 0.001 moles. Now if we compare these two values, we can see that what, the mole of the base is greater than the mole of the acid. So which means all of the acid will be used in producing the salt, and we will still have some amount of base left which will dissociate in the solution. Hence, because the mole of the base is more than the mole of the acid, the solution will be basic, which means there will be what? Excess hydroxide ion concentration in solution after this reaction has completed. So that answers the II aspect of this question. Now let's justify what we just did with calculation, that is the III aspect of the calculation. Okay, so the III aspect, it is telling us to justify the answer in II above, which we said what the resulting solution will be basic, by calculating what the H3O plus ion concentration of this solution. Now, before we do that, we need to know the amount of what we are saying the solution is basic. Okay, so it means what? There is an excess OH minus in solution, so we need to find the concentration of the excess OH before we can be able to calculate the concentration of what? H3O plus. So from what we did in the II previously, the mole of what? OH minus that will be left will be what? The mole of the what? The base, which is in excess, minus the mole of the acid, which is the limiting. So we have the mole of the base that we had initially was what? 0.001 minus 0.0009 for the acid. So the amount of substance left, or the amount of OH minus left in solution, will be 0.0001 moles. Now the volume of the solution, because we added 100 ml to another 100 ml, so the resulting solution will be what? A total of what? 200 what ml or cm cube, which is equivalent to what? 0.2 dm cube. Okay, so this is the total volume of the resulting solution. So it means the concentration of what? Of the OH minus, which is what? In excess in the solution, is equal to what? The mole over volume, which is equal to what? 0.0001 divided by 0.2, sorry. So this will give us a concentration of what? 5.0 times 10 raised to the power minus 4 molar. Alright, so this is the concentration of our hydroxide ion in solution. Now if we have that, then calculating our hydrozonium ion in solution will be easy. We know Kw is equal to this multiplied by OH minus. Now we have 1 times 10 raised to the power minus 14 is equal to, we don't know the hydrozonium ion concentration in solution, but we know what? The concentration of what? The hydroxide that is in excess in solution. So it means we are going to multiply this by what? 5.0 times 10 raised to the power minus 4. So making H3O plus the subject, it means we have 1 times 10 raised to the power minus 14 divided by 5.0 times 10 raised to the power minus 4. So our concentration, if we input this into the calculator, we are going to get 2.0 times 10 raised to the power minus 11 molar. So this is the concentration of our hydrozonium ion in solution. Now if you calculate the pH using this concentration, you are going to see that the pH you obtain will be greater than 7. Now because the pH is greater than 7, we can boldly say the decision we took in II by saying the solution is basic is correct, because a basic solution has a pH greater than 7, and which in the case of this, if you use this and you input it into the calculator using pH is equal to negative log of what? H3O plus, you are going to see that the pH will be what? Greater than 7. So thank you so much for watching. This is just a brief introduction to how to use the formulas to calculate pH and pOH of an acid or a base solution. So thank you so much for watching, and then I'll see you in the next video. Bye bye. Hello and welcome to MyScience Tutorials. In today's video, we are going to be looking at the acid dissociation constant Ka of a weak acid. So what is a weak acid? A weak acid or base only ionizes or dissociates partially in an aqueous solution. So it means a weak acid or a weak base can only ionizes partially, not completely, in an aqueous medium. So which means a weak acid in an aqueous medium, if the acid has 3 or 4 protons, it can only donate 1, 2, or few of those protons to form what? An aqueous solution. Now, let's have a look at acetic acid as an example. Now, acetic acid is of the formula CH3 COOH. This is an example of a weak acid. Now, if it dissociates in water, which is liquid, we have what? The acetate ion being formed, which is CH3 COO minus aqueous, and we have what? H3O plus ions also being formed. Now, the Ka, or the acid dissociation constant of any weak acid, can be written as what? Ka is equal to, now in this case we are going to have what? The concentration of what? The ions formed in aqueous solution, which is what? The acetate ion CH3 COO minus, multiplied by what? The hydrozonium ion concentration, divided by what? CH3 COOH, and that of water. But we neglect that of water, so we have what? The Ka to be what? CH3 COO minus, then H3O plus ions, divided by what? CH3 COO minus. So with this formula, we can easily calculate the Ka of any weak acid. So let's go ahead and look at an example. Example number 1. A weak acid Ha is found to contain 0.049 molar Ha. The concentration of the hydrozonium ion and then A minus ions is equal to what? 8.4 times 10 raised to the power negative 4 molar. We are to calculate what? The Ka and then the pKa of this particular acid Ha. So let's go ahead. So we write solution. First of all, we need to write what? The dissociation of the weak acid Ha. So we have Ha, which we are saying is liquid, plus what? Water, H2O, which is also liquid. Then the reversible sign comes. Then we have what? H3O plus being formed in solution, aqueous, plus the A minus being formed in solution. Now, once we have this equation, we can say our Ka is equal to what? The product of the hydrozonium ion concentration in solution, which is H3O plus, and then A minus, all divided by the concentration of what? Ha. So our Ka is equal to, the hydrozonium ion is equal to the A minus in solution. So we have what? 8.4 times 10 raised to the power minus 4, all squared because they are 2, so we square them, divided by Ha, which is what? 0.049 molar. So we have 0.049 over here. So our Ka will be equal to 0.0000144, or our Ka is equal to 1.44 times 10 raised to the power minus 5. Now that we have the Ka, the second aspect of the question is saying we have to find pKa. Now pKa is equal to negative log Ka. So which means negative log the Ka value, which we have as 1.44 times 10 raised to the power minus 5. So we have 1.44 times 10 raised to the power minus 5. So negative log 1.44 times 10 raised to the power minus 5 is equal to 4.84. So it means the Ka of this acid HA is 1.44 times 10 raised to the power minus 5, and then the pKa of this acid is what? 4.84. Let's have a look at another example. Example number 2. A solution of acetic acid has the concentration of what? 0.01 molar. 4.2% of it ionized in aqueous solution. We have to calculate the ionization constant, or the Ka. So let's go ahead and see how we can solve this problem. So we write solution. Okay, so first of all, the concentration of the acid, which is the acetic acid we have been given, is this. So we have CH3 COOH. That is the concentration of the acetic acid to be 0.01 molar. Now the question is telling us that 4.2% of it ionized. So which means this is before the ionization. After the ionization, what? 4.2% of it ionized. Okay, so 4.2% of what? The concentration of the acetic acid is equal to what? 4.2 divided by 100 times 0.01, and this is equal to what? 4.2 times 10 raised to the power minus 4. Alright, so let's go ahead and write the equation of dissociation of an acetic acid. So we have CH3 COOH liquid plus H2O, which is also liquid. Then we have the reversible sign. Then we have CH3 COO minus, which is the what? Acetate ion, plus H3O plus, aqueous in solution. Now, initially, before the ionization takes place, we have what? 0.01 molar of the acid, and then 0.00 of this in solution, because it has not yet dissociated. Now, during the dissociation process, only 4.2% of the acid dissociated. So which is this? So we have minus 4.2 times 10 raised to the power minus 4, which means it is only this amount that dissociated in the solution. Now we have 4.2 times 10 raised to the power minus 4, and then 4.2 times 10 raised to the power minus 4 as the amount of what? The acetate ion and then the hydrozonium ion produced upon the dissociation of this acid. That is the 4.2% of it. So after the dissociation, what do we have? So we now subtract what has dissociated from this to get what is left of the acetic acid. So if we do that, we are going to get 9.58 times 10 raised to the power minus 3. Then we have here 4.2 times 10 raised to the power minus 4, and then 4.2 times 10 raised to the power minus 4 over here as well. So now that we have this, we can see what? Our Ka is equal to what? We have CH3 COO minus multiplied by what? H3O plus all over CH3 COOH. Then our Ka will now be equal to the concentration of the acetate ion, and then the hydrozonium ions are 4.2 times 10 raised to the power minus 4 squared divided by the concentration of what? The acetic acid that is left in solution is what? 9.58 times 10 raised to the power minus 3. So our Ka value in this example is 1.84 times 10 raised to the power minus 5. So thank you so much for watching, and then if you are new to MyScience Tutorials, kindly consider subscribing so that you don't miss any of our latest tutorials. Thank you once again, and I'll see you in the next video. Bye bye.